What I want to say is that what I'm going to talk about is that databases and categories are very close to the same thing. I can even say are the same thing, but it's not quite true. Nothing is quite true, but I think what I thought was interest in foundations of math eventually became interest in kind of more like the structure of math. What are we doing when we do math? What is legal and what is illegal, and how do you put facts together to come to new facts? In category theory, I learned when doing something called algebraic geometry, which is to connect algebra and geometry together, two disparate fields, that category theory creates a language to connect. And so I realized kind of the power of category theory to say lots of things very easily and to put a lot of information into a very small, compact thing. And that was graduate school, and then as a postdoc, I just as a hobby became interested in kind of what information is. So, you know, we know how to use it, and we know that some people are better at kind of putting facts together than other people. And what are those people good at, really? What is the thing that you're doing when you put together an information? If I have something in my mind, I need to put it into a sentence form, into a string, somehow into a string of sounds, and get it to you. And the syntax and the way that I send that string is enough for your mind to recollect this into a ball, some kind of new concept. So what is that encoder and decoder? In terms of information theory, you see how many ones and zeros might pass through a channel, but that's what I'm more interested in, is what are the encoder and decoder on the two sides? What are their structures? And that way we can kind of think about how information is transferred and maybe put together some of the problems or fix some of the problems that exist in the current system. So what I really want to do is use category theory, because I think it's a good model, a good language for modeling to understand what information is and how it's transferred and things like that. So I would say that there's kind of a lack of coherence generally in information science. So that's something like you have all these databases and they're incompatible. It's hard to load data into a different database, send data, the structures are different. You have different mismatched vocabularies, like say different ontologies. And just generally, one system and another system don't work well together. That's the problem of meeting a new person and not having anything to talk about except the weather. Like you can talk about, I know what an integer is, you know what an integer is, that's great, but can you say, like, I have this system, do you understand what I'm saying? And another person says, I have no idea what you're saying. So how do we, I mean, the internet and computers itself is a way of getting our ideas into a strong form where I can type some things in LaTeX and have this show up. I'm obviously able to communicate with a computer. Can we have different computers communicate with each other? Well, we need to have, you know, the semantic web type idea needs to work. And so I think that what we really need is an overarching framework that handles programming languages, grammars, databases, and any other kind of thing where information is found. So the way I really came to databases from the idea of category theory and information science is I thought to myself, as a kind of naive person, where I know I care about information, where is information found? Where do you find it? Because let's just study it, where it lives. And I thought, well, a database definitely has information in it. So what is a database? Right, so we need some kind of standard, just like a standards body like W3C or something else. I think we need a standard of information of all sorts, and I would say that category theory might be such a thing. So the question is, can math model information itself? And finally, going towards the actual language I'd like to use is category theory. It was invented in the early 40s to relate geometry and algebra. And a lot of people still consider it to be too abstract. A guy named Colin McCarty, who I talked to once, said that in all of his years, whenever, at any given time, he'll talk to people about category theory, and they'll say, category theory is too abstract, there's no point in it. But they're using some category theory. They're using some commutative diagrams or some monoids or some things, and they consider the category theory they know to be, well, that's just math. But any more than that is too much. It's kind of like on the highway. Anyone who's going faster than you is just obviously going way too fast, but you're going just the right speed. So I think nowadays you can barely find in algebra or geometry a paper that doesn't use category theory. And in topology, it's almost become what topology is in some sense. It's just strange. Topology is a theory of shapes, but it's gotten to be quite abstract and quite category theory dominated. So, so as I guess category theory is now useful in computer science. There's a physics paper where they say that, that the reality is a topos, which is a kind of category. Linguistics, they use, what's it called, in semantics, they use the lambda calculus, which is, again, Cartesian closed categories. And I would say, even though I don't know Haskell, people who I know who know Haskell and category theory say that when you're doing Haskell, you kind of feel like it's helping you and that it's the right language. There's something to it that just kind of feels right, that other programming languages, non-functional programming languages, don't have. And I think category theory, I would say the same kinds of things. As you do it, you just feel like things are really working, and you get suggestions like, maybe I should try taking the Grothendieck deconstruction of this functor, or you have ideas that, and things are presented, and sometimes things feel wrong, and you know that that means that you're doing it wrong. So, it kind of, category theory offers an ability to put layers upon layers of abstraction, create layered types, and do it in the correct way that you can be assured of. So if a database schema is a category, then what's the data? The data is a functor from that category to the category of sets. And so I guess the point is that anyone who likes databases already likes categories, they just don't really know it. And anyone who likes categories already likes databases. So let's see how that goes. So the idea of a category is that, I mean, there's a definition that I'll present in the next slide. But the idea is that you have objects of a certain sort that you want to gather together into one category and discuss. So Kant, or maybe even Aristotle, made up the word category. And it's to talk about, I have a situation here. It's the situation, I'm looking at people, or I'm looking at metaphors, or I'm looking at flowers, or whatever it is. And I want to know, here are the things in that category, and here's how they relate. And so in the mathematical definition, you have objects, which are the things in the category, and you have arrows, which is how they relate. You could have an arrow going from D to E and back to D. That might be thought of as like a relationship that's kind of mutual. But at least there's also one-directional relationships too. So you can think of it like a graph or a multigraph, directed multigraph. The nodes are objects and the arrows are relationships. And, but in a category, the difference between a category and a graph, so this looks like a graph, but what's the difference? What makes a category is the ability to say how two arrows compose, how that path is a new arrow. So really, there's two ways of saying it. One is, I have a graph, but some paths in the graph might be equated with others. They're equivalent. Like if I take my data type and I do this to it and then that to it, that's the same thing as doing this other thing to it. And it will always be so. No matter what I input, if I do this sequence of steps, it'll be the same as this other sequence of steps. So in this example, I could say, well, if I go j to k, that's the same thing as I 3 times. Okay, so let's give the exact definition. It's a set of objects which we'll call ob of C. The category I'm naming is now C. And it's a set of arrows called air of C. And each arrow has a source and target. And every object has a primary arrow or identity arrow. I'm not sure why I called it primary. I think identity is a better name, but I guess maybe for relating it to databases later. This is a set, air C, and this is a set, ob C. And I have 2 arrows going from one to the other. And I have also, every object has a primary arrow. It just says, I am myself. I am related to myself by virtue of being myself. It's my identity. And the associative law says if I go from A to B to C and then to D, say, by a morphism called H, or an arrow called H, that it doesn't matter if I compose first and then go by H, or if I go F and then compose later and get to D. Those have to be the same. If you think about how functions work, if you do 3 functions in a row, they're definitely going to be associative. And the identity law says that if I take the primary arrow at A, I stay put at A, I am myself, and then I go to F, that's the same thing as just doing F. And if I do F and then I say B is B, that's the same thing as just doing F. The arrows are functions, ways of assigning to each element of set A an element of set B. Hask is another category. The objects are Haskell data types, and the arrows are the Haskell definable functions. So I would guess that every arrow in Hask is a computable thing. Partial orders can also be considered as categories. If I have the partial order with 4 elements, A, B1, B2, and C, and this relationship, I can draw it by just drawing an arrow from A to B, from one object to another if it is less than the other. So everything is less than or equal to itself. So there's these primary or identity arrows I haven't drawn, and I never draw because they clutter things up. But I also have that A is less than B1, and B1 is less than C, and A is less than B2, and B2 is less than C. And therefore A is less than C. These diagrams both commute. And commute means that this path is the same thing as this straight path, which is the same thing as this bottom path. So here's a graph. It's a picture of a graph, at least, that I could turn into a category either by saying that giving a name to FG and a name to. So to turn a graph into a category, I would say it's a free category, where I just say FG is a new arrow and FH is a new arrow. For every path, I just add a new arrow to my category.
The empty paths.
Including the empty paths. Thank you. Yes. So that becomes a reflexive graph first, and then a category second.
It's only finite paths, right?
That's right. Only finite paths. A monoid is a set with a multiplication law. Free monoids come up if you have 7 letters to work with. Then the free monoid on 7 letters is any string, including the empty string, with those 7 letters. But you can also, the word monoid, well, I don't know if this is true, but at this point at least, the word monoid sounds like mono, meaning one, and it's literally the same thing as a category with one object and probably many arrows. And so what you think of is this category with one little dot here, but lots and lots of arrows, and I only drew one there. But if M is a monoid, its set of arrows is a set, and that set will have a unit, the identity arrow, and a multiplication law, the composition. And that is literally what a monoid is. There's no difference. The only difference is visualizing as a dot with lots of arrows that are hard to understand versus viewing it as a multiplication table or something else. So here I have the natural numbers with multiplication, and what I'm trying to indicate here is here's my one object, and I have infinitely many arrows, one for every natural number. And I want to say that if I go along the arrow called 2, and then I go along the arrow called 3, that should be equivalent to the composition should be the arrow called 6. So the composition law is hard to write down. N times M is NM, 2 times 3 is 6. So the set of arrows is the set of natural numbers. Okay, so now we're getting ready to get to functors. So the idea of a functor is a graph morphism. It's required to respect the composition law. That's the extra important thing. So what that means is a functor from one category C to another category D. I'm going to think of C over here as a set of dots and arrows, and D over here as a set of dots and arrows. And what this functor has to do is take every dot here to a dot here, and every arrow here to an arrow here. And if this arrow goes to, if the arrow goes to this arrow, then the source dot must go to the source dot, and the target dot must go to the target dot. That's what I mean by the source, that these functions should respect the source and target of every arrow. The primary arrow from A to A over here should go to the primary arrow from F of A to F of A over here. And the composition law should be respected. So if this path is equivalent to that path, then so should be on the other side. So an example of functors, for any category C, dots and arrows, the identity functor is obviously, it just takes dots to dots and arrows to arrows and respects everything that it could possibly respect. Take the one-point set and take everything in C and just send it to that one-point set. That's another functor. It's kind of just very destructive functor. Everything is gone, but it's just saying it's kind of constant. This could have been replaced by the set of natural numbers, and it would be another functor taking C to set. Every Haskell data type, it's a bit confusing to consider the Haskell data type versus its instances. So for example, the data type integers has as instances all the integers, but I'm distinguishing between the data type int and all the integers. So instances is a functor. It takes every Haskell data type to the set of instances of that data type. But this functor, there's a couple possibilities. No, there's only one possibility. I must send there's several possibilities. I must send A to C because objects must go to objects, and B must go to C. But F could either go to G or an unpictured arrow like the identity or something else. But objects are going to objects and arrows are going to arrows. And finally, cat itself is the category whose objects are categories and whose arrows are functors. So you package this entire category of dots and arrows into one dot, and you package this entire category into one dot, and a functor between them contains a ton of information, but I think we're probably used to that. Set is a category, cat is a category, and there's a functor from set to cat. For example, I can take a set and just consider it as the category with that many objects and no arrows except for the identities. There's a functor from post-set to cat. I can take any partially ordered set and write down all the elements of it as objects and an arrow when between 2 if A is less than B, less than or equal to B. And there's a functor from graph to cat. I can take any graph and I can write down the free category where every path counts as an arrow. But going back to monoids, if M is a monoid, then what is a functor from M to set? It's called an M set. And the idea is that there's a unique object in this monoid M, and the image of it is some set. It's got to be some object in the category of sets. So the functor, the first part, sends objects to objects. So now I have a unique object, S. It's a set. And for every arrow in M, I get a function from that set to itself. So we call this an action of that little M on S. So, yeah.
What do you mean by the image of an object?
A functor takes objects to objects, and where an object goes, I call the image. So I have this set with some kind of operation on it. And the operation, I give you any element of M, and that operates on the set. And so a finite state automaton is an example. So S would be the set of states here, and M is the monoid of strings in your alphabet. And a curried version of F, like if you kind of think it through, it'll be the state transition function. I have this set of states, and for any string of letters in my alphabet, I can go from one state to another. This will be an action of M on S.
I guess there's only finite state if you choose a finite set.
Yeah, I never had to say finite state. You're right. That would be to finite set. Good point. The last thing I want to say is, before we get into databases, so this is the kind of the technical category theory part of the talk, is that you can turn a functor into a category. So it's called the Grothendieck deconstruction. Grothendieck is a famous category theorist and algebraic geometer. And so suppose we have a functor from C to set. It doesn't work for every functor, just from C to set or from C to cat. But what you can think of this as, C is kind of a model, and set and F is its instances. So for every object in C, I get a set, the set of instances or values of that object. And for every morphism, I get a morphism of sets. So here's an example of a category, 3 objects and 5 arrows, 3 of which are identity. So these 2 arrows, F and G. And F, I need to tell you where A goes. What set is it? Well, it will be the set with 3 elements. And B, I'm going to send to the set with 2 elements. And C, I'm going to send to the set with 1 element. And F, I'm going to send A1 to B1, A2 to B1, and A3 to B2. And I kind of label that there in that way. And the function of sets from here to here is obvious, because there's only one possible way. So this is F is a functor from this category to sets. And the Grothendieck deconstruction of it, it just writes down all these dots and forgets where they came from. A1, A2, A3, B1, B2, and C1, and just where they all go to under these various maps. If you wanted, you might call this, the 3 maps here, here, and here, F, and the 3 maps here, G. Just give them all the same label, even though it's not quite legal. But that's kind of how you think of it.
Why is this interesting?
Why is this interesting? It's a very, first of all, set is kind of a foundational category. It's a very important category. As he was saying, a lot of category theory is founded on sets, and so is mathematics itself. And functors are the business of category theory. It's how different categories relate. And so having a functor from your random category to set is kind of a first thing that a person might think about, or a first thing that one might explain in learning about category theory. But what's amazing is that you can turn it into a functor. It's kind of like totaling a list, or flattening a list. You have this thing. If I had the category of natural numbers, I would literally get a list. If I had kind of a certain category, A to B, B to C, or A1 to B, A2, A2 to A3, A3 to A4, dot, dot, dot. And a functor from that to sets would literally be a list. And this would literally, well, what would this do? It would take the list and turn it into a linked list. Okay, so that's the end of the category theory part. And now I'm going to get to the database part. So what's a database? A database consists of a bunch of tables and relationships between them. The rows of a table are called records, tuples, or instances, and the columns are called attributes. And any column of a database or any table could either be pure data, like first name, David, or something like that, or it might be a key, a primary key, meaning this is the name of this row, or a foreign key, meaning go to this row of this other table. And so in this talk, and to make databases equal to categories, you need to say that every table has a distinguished primary key column. You don't get to just, so-and-so doesn't just get to choose their primary key column at any given time and say, I'm going to take these 4 columns to be my primary key. So foreign keys, here's an example of 3 mathematicians that work in a department store, of course, because that's what databases are, department stores, apparently. So, so here are the primary key columns. I did note them with this double line, 101, 102, 103, and X02 and Q10. And here are the records, or rows. You'll note that MGR is a primary key column that relates employee back to employee. So David Hilbert's manager is Alan Turing, who lived much later, but okay, not too much later, I guess. Bertrand Russell's manager is Bertrand Russell. Okay. And David Hilbert works in the sales. No, he worked in the.
Bertrand Russell's manager should not be Bertrand.
Okay, so Bertrand Russell works in the production department, and David Hilbert and Alan Turing both work in the sales department. And the sales department secretary is David Hilbert, and the production department secretary is Bertrand Russell. But you might want to enforce certain constraints, because in your database, you want to make sure that if you're the manager of a certain employee, then you're in the same department as that employee. You could make that constraint. And I don't know what that constraint is called in database theory. It doesn't seem to actually be something that it's not called referential integrity, but it's some kind of integrity constraint. You also might want to say that if the secretary of any department works in that department. So let's see, Q10 secretary is 101. That's David Hilbert. The department of David Hilbert is Q10, so that works. And the secretary of production is 102, and 102 works in production, so that works. So you might want to enforce certain things like that. But the last thing, I try to think about why this wasn't recognized before, as far as I know, that databases and categories are the same thing. And I think it must be the data columns. But theoretically, you can consider even a data column, a data type, as a 1-column table. So for example, car4, 4 characters might be AAAA, AAAB, Alan, Aleo. So any data column can be considered a foreign key to a 1-column table. And so a foreign key to this table just tells you what row to go to, but the row to go to is the data itself. Go to row Alan. So my conclusion here is that every column in the table is a key. One of them is primary and the rest are foreign. So here in this example, that's primary and that's primary, and these are foreign as they were before, but this is foreign to a 1-column table of strings, as is Hilbert, or first and last are foreign key columns to a 1-column table of strings. So here's a picture of this database. Manager is an arrow from employee to employee. It's a foreign key. Employee's department is called DPT, and secretary takes department to employee, and first and last and name are arrows to string. Those are the foreign. This is the database schema. This, as you can see, this lower thing has no data in it. It's just the schema of something. It's just the layout of this. So the objects in this category are tables, and the arrows are columns. It's not really just the column, it's kind of where the column goes to. So the primary key column of a database, of any table, is the primary arrow or identity arrow of that object. And declaring integrity constraints like manager composed with department equals department is declaring a composition law. You can declare any composition law you want, and you can just say, I need my database to conform to that. So when a person makes a database administrator, they have an ER diagram or some kind of diagram of how the tables are supposed to link together. And it's important to them to know that this column is not just the number 103 or invoices or something like that, that is actually linking to the manager table or to the employee table. And they will write that down as a database administrator. They will not allow you to just think of this as a number. Okay. Okay. Morphisms of schemas. Well, that's just something that you would first think to do if you were, if databases are categories, then what's a functor between categories? If database schemas are categories, what's a functor between schemas mean? Well, here's a schema where I don't know departments, and here's a schema where I do. And there's a category of data sets on C and a category of data sets on D. Kind of like all the ways of filling in my schema with compatible data, all the ways of giving it semantics. I can call that data sub C, just for lack of a better name. What it says is if my database has no department, then I have a functor from my database schema to yours. And any data you have, I can just pull back in an obvious way, just forget the department. But this doesn't really show the power of this idea. The power of this idea is that functors can get very general. It's nice to have some kind of provable, high assurance, whatever words you want, to say this is definitely going to work. This is what it's going to do. By the way, there's also functors called G lower star and G lower bang that take data sub D to data sub C. So there's actually canonical ways, if I have data here, to send it over to your schema. Although those are I would like to think through those a little better to see if they have real-world meaning. I think that they will, but what they're often going to do is just make new strings that never existed before and kind of like create new objects to fill in what they have to be. But the point is that there's lots of ways of taking data from one database schema to another in very mathematically rigorous ways. So next thing I want to talk about is RDF, which is a semantic web term for a graph of data.
Sorry, I was thinking this looked a lot like semantic web. So.
Okay, good. Here we go. So given a schema C and data, F taking C to sets, we can apply the Grothendieck deconstruction to F. So as I said before, this is a thing that you'd want to do generally for a functor from C to sets. You'd like at least want to know what that would do. Every row, what would happen is that every row in the employee, department, and string tables would become a vertex in this new RDF graph.
Just back up, I'm just
Sure.
still with the previous slide or so. My experience when I've been using functorial semantics for things is that on real computer systems, the thinking about it in terms of category theory gives you, you sort of see in some sense what it ought to have been, but it wasn't really quite that.
Yes.
And so that's what we have in Haskell. So polymorphic functions are very close to being natural transformations, but they're not quite. And a bunch of things like that. So in your experience with databases, do you find that, you know, if you think about the functorial semantics, there's a sense of, in an ideal world, the database semantics should be this functorial semantics, but in practice it fails for the following reasons?
It fails in that, you mean how the practical version fails to be as nice as the theoretical? I would say the fact that these constraints are comments. The fact that the secretary of a department must be in that department is not part of the schema, is like drawing a graph and then writing as a comment how it's a category.
But that doesn't stop it being functorial. It doesn't stop it being a categorical semantics.
Well, it's more
differences in behavior from like the practical world to the.
I mean, one problem is that there's no framework that everyone uses. Some people allow foreign key column, primary key columns to be 2 columns of the table. Or some people say I can pick whatever one I want to be my primary key column. Whereas for me, I'm fine with that, but I'm going to need morphisms between the two that connect one table to another, which one is a primary key column. And so I would say, I mean, that's one thing I can say. To be honest, my work with databases is mainly theoretical. I've seen real-world databases before in my life, but less than 5. So I don't know exactly how they work, but all I've been told is that they're horrible in practice. And so since categories are beautiful, there must be something going wrong, and I don't know what that is exactly, but I would like to know. I talk to database administrators a lot, and they're very happy with this, at least the one I'm talking to most often. But it's hard for me to get at exactly what is wrong with the current model.
What about the other database operations?
These are things like fiber products, and there are also things like certain pullbacks. which I don't have on this slide, but I would have to talk. I think we have some kind of informal discussion time later in the day, right? There's ways of kind of putting all the things you want to join in a schema, and then sending it to something where the ones that you want to join are now the same dot. The same two objects are going to one. If you push forward along something called G lower star, it will do a join.
Right.
If you push forward along G lower bang, it will do it'll only work for like schemas that are more related, but it'll insert or union columns together. And also in databases, in reality, you can declare a certain table to be the union of two others or the join of two others and have that in your schema. And to do that, it's not really a category anymore. A database would now be something called a sketch. But these are well-known things and very interesting things. Yeah?
So back to normalization. It seems like normalization is about changing schemas. But I think your formalization here assumes a degree of normalization. Like,
It assumes exactly the amount of normalization that a category is,
exactly.
I suppose, yes.
So an unnormalized database is not going to be normalizable using morphisms of schemas, you know, because it's like, whoa.
It would take some work to turn it into this, is what you're saying.
I think just an unnormalized database just ain't going to be a category. So you can talk about normalizing it using morphisms.
Well, I think you could always add a column of synthetic primary keys to every table, and then you could throw out the existing primary keys, and that would give you sort of the free normalization.
Well, I guess some normalizations that would work for, but others, like, you know, if you had a very poorly designed database where you had the name of the department in every row, and some of them were misspelled and so on.
That would be really actually fine because, I mean, in reality, one of the big differences, I mean, that stops me from saying that a database is a category, and I have said that, so I'm kind of lying. It's really more like a sketch or a graph sketch in that I don't write down the column for secretary's first name in my department table. But if it really is a morphism from D to S, if I do S, if I take little s and then F, first name of the secretary, that actually should be a column in my department table. That'd be an unnormalized database in your kind of sense.
Yeah.
I don't write that down because I know that it's the free composition. In other words, I don't need to write it down because I know how to get there. And a sketch is basically a graph where you only say what diagrams you want to commute, you don't say the other ones, and you kind of assume that every other path is just freely composing. And so an unnormalized database, I think, would be something more like actually what a category might be. So in some sense, I mean, it's an interesting point. What you want is a graphical model of a database. And what happens is that the rows become the subjects, the cells become the objects, and the column names become the attribute names. So last would be an arrow from 101 to Hilbert, and that's exactly what happens in the Grothendieck deconstruction. 101 is being mapped by first to David, last to Hilbert, manager 103 in department Q10. And I didn't draw 16 other arrows, 12 plus 4 other arrows in here that I could have drawn. Okay, so that's the RDF graph of this. Of course, it'd have way too many elements in it because it'd have one for every possible string or maybe every possible URI. And maybe I just want the ones that have ever been instantiated before instead of all of them. So actually the first database you ever saw, and the first category you ever saw, first database you ever saw was a multiplication table, and the first category you ever saw was a multiplication table, that monoid. And so this literally is the application of this idea to that setting. Okay, so blah, blah, blah. I mean, there's something good about this is what I'm saying here. So, but category theory is designed for levels upon levels, mapping databases to databases and what happens in the relations, what happens in the tuples. And so what's interesting is, it could be useful in practice, and a case in point is people are interested in relating relational databases to RDF, and that's just a kind of obvious thing to do. It's the Grothendieck deconstruction. And finally, well, Hask is a category, and values taking Hask to set is a functor. So you could think of Haskell as a database. Each type would be a table, and every function between types would be a column of that table, with column in table A with values in B, and each value of type A would be a row, and then the R, C table would be its image in the other table. So it's just, there is a way to think of Haskell in that kind of way. You'd never want to write it all down, but it exists. It's theoretically there. And the point is that any other database in the world could be considered as a category of user-defined types rather than Haskell types. Instead of God-given, they're man-made. But now defining Haskell functions on these types kind of would just connect database category with Haskell category, and it'd be a very kind of, things would flow in a nice way, perhaps. I haven't worked that out at all, but I just imagine that if the two things are categories, instead of thinking of them as very different things, and they're just the same thing, it's rather user-defined types rather than God-given types. So the point being that databases and programs could hopefully be smoothly integrated. And that does it for my talk. Thanks.
So there are some attractive aspects about using natural keys.
Using what?
Instead of natural keys in database instead of these synthetic
Uh-huh.
numbers. But natural keys often means that you need many fields to make up your keys and primary keys. So what are the challenges with going away from just having one field being?
A lot of times I would guess that natural keys could either be constructed as, putting dots or semicolons or some kind of chosen character, and make a primary key column that you can parse into those 4 columns, those natural key columns. But I think what you're saying is that you don't necessarily want to do that. I'm not sure. I'd also, so I'm saying I think there should be a way of doing it using primary key, a single primary key column. And I'd also say that it seems to me that a lot of those are join table, are somehow product tables of other. If you need three things to declare your key, 3 columns, then perhaps your table is the join of 3 other tables or something like that. And that you could, I have a feeling by how you're looking at me that I'm not answering your question.
So that makes me wonder kind of how algebraic data types fit into this, because all of the data types that you're talking about here are sort of flat in a sense,
Right.
You could say that one of the values of these is actually a tuple, but in a sense it's sort of a flat tuple. You're not looking at it as having parts. But if you have something where you have data types that are made up of alternatives, which is basically what you've got, you've just got a list of alternatives, but you've also got some sort of notion of products, so you can build up structured data out of that. Then I wonder if that actually just fits into here nicely, that those become separate tables that are...
I mean, all I can say is that I would hope so, and that I will work for that. That's what I want, is that anything that you could do. For example, here's something I don't know how to do. There's something where you have something called calculated fields. You have a kind of a detail table and a master table, where like this one is smaller, but this one's got all the details in it, and they all map, like different rows are grouped into different places. And what you can do in this master table is you can say, take everyone whose first name is David, you get a huge list, and now add up their salaries and put that here. What that looks like is something I don't quite understand. It's something that a topologist would call integrating on the fiber. So you have some map between topological spaces, and for every point here, I look at the fiber and I add it all up. I integrate that. I add up the area of that place, and I consider that a new function from here to something. But how to make that category theoretically rigorous, I think, is the kind of question you're asking, and I don't know that yet. It's something I want to understand better.
Because once you
I
get
think
that
one
sort
thing
of...
that Magnus, that I got from Magnus's question is there might be a distinction in this category framework between sort of tables that actually are physically present in memory versus sort of virtual tables that are just part of the category construction.
Like the table of strings or something.
That's right, that actually don't, as a computer scientist, you're sort of trained to think about what's the actual data being stored in, say, disk or whatever.
Right.
So when you sort of say there's a requirement, for instance, that there be a unique key column for any table, that might be okay if it's a virtual. If that's a virtual column, doesn't actually show up historically.
That's right.
And then you actually just talk about the relationship between this virtual key column and the actual physical columns that say make up the natural key.
That's right.
You can
And
make
then
some...
those would actually have physical storage.
You can make some conclusions about physical storage pretty quickly. Like you can trivially show that any object in the category that doesn't have arrows coming from it.
That's right. Is it?
Need to be
That is right. That's exactly what I think of it as too. I call those terminal tables, even though that's not good category theoretic parlance or terminology, because they're kind of terminal symbols. If you think of context-free grammars or something, they're kind of the end of the line, and they don't. What you can tell is they don't have any maps out of them. Although you might want to have a map from integers to integers mod 2 or from integers to ASCII, and even though you have ints, you might want to map out, but maybe, I guess, well, I don't know if everyone can see this, but you could have your integer as an algebraic thing mapping to ASCII, but you could also have it mapping to just the table of quote integers or something, where these are just numerical strings of, and so you can deal with things. This is literally your terminal table, and then you have something else with a column of integers that you might want to turn into ASCII later on or something else, but there's a lot you can do in that kind of way. Yeah.
So, okay, so if we take the categories or databases, are there any, so clearly some categories would correspond to really weird databases, like the category of sets.
A huge database with millions of columns, and yes.
So which of the categories correspond to actual databases?
Finite categories.
Well, even finite ones, is that the only restriction to make it like something that we might actually call a category as a I mean, because like the same with Haskell, yeah, you can think of it as a gigantic, table of all possible functions you could define.
Right.
But is there any more structure than just being a category that would actually make it into a database?
I would say what's called a sketch, I think is what you're saying. Sometimes you don't need to, the secretary's first name does not need to be a field of department. My department's secretary's first name. I know that it's, I don't need that as a separate column. And so I don't need what's called free compositions to be listed as compositions. And a sketch is basically saying I have a graph with some declared compositions, but not all of them. I think that might be answering your question, but definitely the finiteness is a condition because you don't want infinitely many arrows coming out or into anything.
But finiteness of how many that would be correspond to finiteness of the schema, kind of, right? So
yes.
You don't want finiteness in the values.
Or finiteness in the values. You don't want finiteness in the values?
Well,
depends if you want to write it down ever or not.
Kind of, but okay. I mean,
yeah.
If you're going to run it on a computer, they have to be limited, but you kind of think of them as being infinite, right?
Yes.
I think we've got time for just one more question.
I don't know if I can fit just one. There's one thing that comes to mind is Conceptual Mathematics, a book in the
Oh, it's a nice
90s.
book, yes.
So trying to relate that to common problem-solving tasks and also kind of the way people think about problems and solutions. But that brings to mind, for your question, maybe the usefulness of a choice function to say, this company only really cares about people in this small universe, or something simple like that. To be able to formally say, we are actually talking about some finite set of what matters, and being able to capture that. And I guess the one question I did have was, I wanted to mention those two things, but I had previously done work in category theory and had not really turned into a concrete paper, but I was interested in information preserving transformations.
Mm-hmm.
And I'm wondering if your ideas about formalizing schemas and formalizing maybe schema changes might lead to a way of expressing, like in the manner that we look at like a git change in a source change management or something like that, allow us to be able to say our information is changing in these steps, and these ones are adding information. These are maybe refactoring, maybe they have to do more with implementation style, and these are actually throwing away information we don't care about anymore. Being able to represent that, know that formally without having to go in there and say, write comments.
That's right. So if you have a database schema, then you can add data. So natural transformations, these functors are data, filling it with data. Natural transformations of functors are kind of inserting data or projecting data in some way.
Turning all your names into uppercase or something.
Yes, those would be natural transformations of functors. So what those preserve and what they don't, well, are they injective or surjective natural transformations? On what subcategory are they injective or surjective? Also, you could take products of these natural transformations, and refactoring, I think, is more like changing the database schema, taking another database schema, mapping it in and pulling back the data, or then sending it somewhere else. I'm not sure what refactoring is, but I've heard just 5 minutes of talking about it.
Kinds.
There are many kinds, yeah. And it'd be nice to kind of think about each of them as whether they fit into this model or not, and how so.